Hello, everyone. Welcome to the second IMA data science seminar this semester. I'm introducing Wuchen Li, who is an assistant professor at University of South Carolina. His major research interests lie in optimal transport, mean field games, and machine learning. Now, he's going to talk about information gamma calculus, convexity analysis for stochastic differential equations.
Okay. Thanks a lot for watching and all your invitation. It's my great pleasure here. This afternoon, I want to talk about the so-called information gamma calculus. Essentially, it is a so-called convexity analysis for some convergence of stochastic differential equations. Okay, this is based on joint work with one of my collaborators, Qi Feng. Now he's an assistant professor in Florida State. Let me briefly talk about the motivation. Okay. So essentially, in modern areas, we have so-called AI sampling problems. Oh.
Yeah,
it's a post.
Can you stop sharing and then restart the sharing?
Okay. Share it.
Yeah, it works now.
Okay, now it works. Okay, very good. So basically, the AI sampling problems is kind of there are many different applications. In the I think 5 or 6 years ago, the so-called self-learning, they try to play the chess or play this Go by this AI type of methods. Now, later on, people introduce so-called generative adversarial networks. It's kind of from-to type of way to transform images and create generated new images. Okay. Now, in biology, people call the protein folding problems. It's kind of way of create different, proteins. And more mathematically, so-called we call it the so-called Bayesian sampling problem. It is a way of computing some parameters given by the distribution. The distribution can come from some inverse problem or coming from some parallel differential equations. So all of them, essentially, I all call them the so-called AI sampling problems. Now, the main goal here is try to sample the images from the so-called distributions. Okay. So essentially, think about this problem. You have lots of images, right, from different shapes. But essentially, it is you can view it for each image as a sample. Okay, your sample space is very large dimension. Let's say my image is in R, it's like 32 times 32 resolution. Now my space will be R 32 times 32. So it's really high dimensional space, and you want to create some samples according to certain distributions. So this is a very, this is the ultimate goal in this AI picture is like I want to create new samples according to certain distributions. Okay. Now, more recently, this you must have heard about this ChatGPT or this kind of reversible diffusion type applications. It's essentially also you want to create something micro chain. You want to go back and forth. In the end, you want to create new images you never seen before. Okay. So basically, I want to say all of these problems go back to this some stochastic differential equation, and you want to create a new algorithm, give a fast convergence, and have some nice properties. Okay. Of course, there are smarter way to build this chain, and you want to approximate the chain efficiently. Okay, sampling efficiently. So now let me summarize. Now we are in the math department, right? How our math people jumping into this field? Application side, you can always compute, build your model, and do the computation. In the math side, we want to ask some mathematical question. So let's make the problem simple at the beginning. Give you some function v, mapping from your domain omega to R. Now the problem is I want to create some distribution pair of x of this shape 1 over z into negative v. Now here your x can be in a discrete space or continuous sampling space. Okay. A pi is from now on, I always use this pi called the so-called target probability density function. Z itself is a normalization constant, which means your total mass of the pi is 1. Okay. Now, what's the point here? The point here is like we want to design fast, efficient, and accurate algorithms. Okay. Now I will have defined what do we mean by fast, what do we mean by efficient, and what do we mean by the accurate. Okay, so we have used some mathematical way to justify it. The second problem here is you want to sample a high dimensional problem. A high dimensional means usually the n is larger than, much larger than 3. For example, for the images, it's R64 times 64, or 32 times 32, right? A high resolution image means high, even more higher, sample space. Okay. Sometimes if you're on discrete domain, you may be 2 to the power 10 or 2 to the power 100. Okay, so this is also very hard dimension. And in many times, your V, following this formula is negative log pi minus log z, is also unknown. Even it's known, it's with some intractable formulations. Okay, that's why usually coming from the Bayesian inverse problem. So in this talk, let's make everything simple. Okay, let's assume V is known, and you know the analytical formula for V, but for the normalization constant Z, you don't know. Okay, or it's hard to. You have to do some integration. It's hard to track. Okay. Yes.
Started for parameter of generation, and now this is not the parameter of generation. Like,
yeah. Well, the generation here means the following: your target distribution pi. Suppose your data follow some distributions, which is
you don't
pi.
know it, right? It's not. You just talk about the sampling issue, but
yes.
You don't solve a generation problem.
For generation problem, you need more steps behind it. You want to learn what is the V. What is the pi behind it?
So you're not going to do it here?
Not here, okay. not in this talk.
Okay. And a small comment, you may move the screen sharing icon.
Oh, that's I want to move it actually. That's how to move this.
Yeah.
Right.
It's okay, yeah.
Okay, if we should move.
I think that will just collapse soon.
Okay, hopefully. Okay. Now let's make the thing much clearer. Let's consider so-called the stochastic differentiation of this form. X dot equal to bxt plus square root of 2axt time Brownian motion. Here, x is in the dimension of Rn plus f. B is the so-called drift vector field, and A is so-called diffusion matrix function. Here, I want to emphasize A and M here means that my diffusion matrix can be degenerate. So essentially, M is larger than 0. So essentially, you have a degeneracy in your diffusion matrix. Okay. One typical example here is the underdamped Langevin dynamics. Okay, the A could be 0, 0, 0, 1. This kind of. Okay. The BT of Rn is the standard n-dimensional Brownian motion. It's a very standard stochastic differentiation. Now the game here to follow this sampling and target distribution follows. For given diffusion matrix and the drift vector field, assume that, okay, this is some mathematical condition I'll give you later. B and A will admit an invariant measure of shape pi. Okay. Now the game follows. Can we analyze the convergence speed for your stochastic dynamics towards your invariant distribution? Okay. Basically, you can create many stochastic dynamics. Its invariant measure is the pi, right? Which is what we want. Now, which one give you the fast convergence rate? Now, that's the ultimate question. Okay, but in this talk, I will tell, give me a B and give me a A. I'll try to create a way to give you a algorithm. And understand this convergence rate is also important to design different markers for change. Either you want to get a fast reversible diffusion, or you get a faster way to create, generate models for this approximation step. Sorry, for this optimization step to figure out what is the pi. Okay, so to do this, this is the older game. Many of you guys know it. Definitely, only know it, right? You know, it's also expert here. So it's so-called optimal transport, mean field control, and information geometry. So what is it? So essentially, you want to find a way to measure. Let's see, how do I know I convert? I have a lot of samples, right? I have stochastic differential equation. So it's a lot of samples. How do I measure the closeness between my solution, the samples to the target. You have to define this. Now, one way to define this is by the so-called the entropy. It's a very classical concept in this area. So essentially, you want to give your distribution E given by samples, given a target. You want to find a way to measure the distance, a distance-like formula between P and okay. So that's the game. It becomes a value, right? How to do it? This is a very long history. People use the Euclidean distance. They define some quadratic formula, and people use so-called entropy. Okay, this is the main target we'll talk a lot. In particular, over here, so-called the Kullback-Lieberger divergences. It's a way to measure. Let me write it here. So the particular distance I call the KL divergence is given by the follows: P of log P over pi. Yeah. This is a particular function you can measure the closeness between the current density function and the target. Okay, and you can show it is non-negative and a lot of nice properties, and people can generalize it to many other so-called information divergence functions. And if you work on this machine learning literature, you will see this all the time. People create different, objective functions, try to do minimization, just this table. Okay. Now, more particularly, starting from 1998, the optimal transport is mean-field control joins into this picture, starting from the computer science. But essentially, it's a math problem. Later, I'll show you. This is essentially a math tool for us to understand the stochastic algorithms. Okay, in a much cleaner way. Anyway, this is the picture. So using this kind of distances is a way to quantify how close between your samples or probability, current probability to the target distribution. Okay, so this is some really important.
Sorry, I'm confused with the big picture. So the P is the solution to the SDE, or
the P is the probability function of your stochastic process. Let's say xt, right? I want to write down it in probability sense, so it's pt. It's a probability of your stochastic process. It becomes deterministic. Okay. The goal of this picture here means that I want to control my stochasticity. Everything become a deterministic. Deterministic means the probability. Okay. Even my question, when I ask question, I don't ask samples, I ask probability. Pi, right? Pi is given or pi is not given. Now in the math, we are interested in how you quantify things in the sense of probability. Okay. Now once you are in that picture, everything deterministic, we can use our tools to try to analyze it. Very good. Now let me give you one example before I talk very general my result. The very well-known example is called Langevin dynamics or overdamped Langevin dynamics. Now in this case, your B is negative gradient of A. A just identity matrix. Okay, there's no degeneracy in the system. Then let's say why this dynamics is important. I will say if you use some numerical scheme to compute this algorithm, compute this stochastic differential equation, you will do the sampling job because in the end, your xt will converge to a distribution with the shape of pi. Why? Let's do some so-called you write a rho tx of the probability density function of xt, which satisfies the following the so-called Fokker-Planck equation, right? It's the Kramer-Goff-Fowler equation. And you write it down and you solve the stationary solution, which means partial t rho equals 0. Its solution is essentially pi equals 1 over z into negative v. Okay? Z itself is so-called normalization constant. So it tells you for this equation, its invariant distribution is essentially the pi. Okay. And this is very important. This is the building block for all the diffusion related algorithm. Okay, this is the first example actually, which works. And it's very simple because A is just constant, B is just a negative gradient operator. Okay. Now, to understand the convergence rate is the other story, right? You want to just at the beginning, if you look at stochastic dynamics, you have a lot of stochasticity, you have a lot of samples. Now let's try to understand in the density level what happens. the tool we can use, since we learned a lot of optimization before, the tool we use is so-called Lyapunov, methods. We all know in the optimization people, and also dynamical theta, this kind of study. So now to study the dynamical behavior of rho, which is the density of your stochastic process, we apply the so-called global Lyapunov function. The global means that, so in optimization, this is the fact. If you want to get to the convergence, you want to get a global convergence, which means the solution. When you want to say some algorithm is good, you don't want it depend on asymptotically depend on pi. You want for any initial distribution, it works. Okay, so you want a global analysis to say how much your density will cover the target. So that's the goal. Okay, so now this KL divergence do this job. Let's do this KL divergence as a rho x log rho x over x. We will see this content a lot along this talk. The first order dissipation tells you d over dt KL divergence along this Fokker-Planck equation, along the density of your stochastic differential equation, will equal some negative value. Negative or greater than log rho over pi squared times rho. Okay, so it's something positive, which means this quantity will decay along the dynamics, which means your rho essentially along this probability trajectory, along this, the density of your trajectory will essentially convert to the, the invariant distribution. Okay, so basically you will create samples according to the distribution you want. Okay, now this is called the first order dissipation. However, this thing somehow is good. I mean, if you have this, tell you your algorithm is good because you have some demonstrate at least for each step your KL divergence decay, right? But in optimization side, when algorithm design side, it's not satisfactory because we want some globally convergence rate, which means I want to know how fast this goes, right? Now, to how fast it goes, we need the second derivative along the trajectory to say what goes. Okay, so essentially you can believe if this p is a function of t coming from your solution, this is just a function of f of t, but it's time-dependent function, right? You want to say, okay, the convexity, the second derivative will tell convexity of this function, right? So you want to say, okay, f of xt, what is the behavior of this? Is this O of into negative t or it is O of t, 1 over t, right? Different function of t means different convergence speed. We want to get this out. If we can get this out, then we can try to build a much better algorithm if I have some parameter to talk. Okay, so this is the game. Now the second derivative is this, the title of my talk. So let me for this overdamped Langevin, it has a closed form solution. It's something squared. Okay, don't worry. And you get the so-called negative Hessian of log pi. Okay, negative Hessian log pi times, this is a matrix product. This is a vector with a log rho pi times with log rho pi. This is the product of this. So it basically, and this is something positive. So basically, if this one is positive by some number, okay, if you know it's definite, then you can control the speed. So
can you elaborate more on this gradient x slopes? I don't understand what's the operator inside.
Okay, so essentially this is a negative Hessian log over pi, right? Times basically let's call it this A transpose A. I write it as rho over pi. Sorry, the pi times A over A. That's my notation. It's just a matrix of some vector. Okay, so before I go, I have to say, once you do the computer science, we do a lot of AI. Every sentence I'm writing here has a name. If you know this name, you can read their papers much faster. Okay, so log rho over pi, in particular log of rho called the score function. Okay, so for the score function is the so-called derivative of the KL divergence. You take a derivative, you get a log rho over pi plus some constant. Okay, and the dissipation of KL divergence equals something negative. That one is called relative facial information. Okay. If you look at the paper, you will see this name all the time. Just make a note and record these names, then you will see a lot of mathematics behind them. Okay. Now the second derivative is something tell you the convergence rate. Now, what can we say? So if the negative Hessian log pi is bounded by some lambda, then people call this log concave sampling. Okay, if your pi satisfies this, then it's a log concave. Okay, log lambda concave. Then your second derivative is bounded by first derivative, and by integral parts, by the integration of time variable, you can prove the so-called exponential convergence rate, which means this function is essentially e to negative lambda of t. Okay, lambda is given by the negative Hessian log pi. Your negative log concavity tells you the convergence rate for a very simple overdamped dynamics. Okay, so this is a common knowledge a lot. I mean, in the statistics computing community right now. Now, my question here is, can we make it more general? This is a very simple dynamics. It works. Now, if I have a general drift function, I have a general diffusion matrix, and then my diffusion matrix is also degenerate. Can we do the similar job? What is the negative log concavity? Okay, that's this talk about. Okay, a little bit technical, but essentially the idea follows. For simple case, this current analysis works. Now we try to build convex the negative log concavity for general stochastic differential equation. If it works, my currently ongoing project is like to build a fast convergence guaranteed algorithm using this analysis. Now, this current analysis never be, everybody in the field, in the math department studied this before, okay? So the number one thing people say this is so-called log Sobolev inequality. By the growth is probability guy. The log Sobolev means essentially, it means, okay, I want to bound this to kill and the derivative kill. But essentially, if I know the log concavity, I definitely can prove log Sobolev. Okay, so this in the log Sobolev somehow it is in optimization is so-called the I forget the name, the PL kind of condition. If you are familiar with optimization, you know this better. Okay, so the game here is how can we establish log Sobolev and not I assume it. Okay? So this is important. Then how do we compute the negative concavity? The negative log concavity is so-called iterative gamma calculus. It's just a way you want to derive the convergence rate. It's by Beckery, Emery, Breton, and Gaffrey-Fellow, so on and so forth. Now, for general dynamics, for nonlinear PDE, people also studied it before, so-called entropy dissipation and the Harper constativities. I have to make sure, like the guy here, like Vallani and Mohout write a book. In particular, Vallani write a book on this direction. However, his analysis is only 1 over T to infinity. He cannot prove the exponential convergence rate. Later, I will show several examples we win towards his result. Okay. So, and many people in this open transfer study this problem, but for very general A and very general B, it's still open. In particular, A is degenerate. Now let me state my problem more clearly. Recall that I write on my dynamic follows: x dot equal to b xt plus square root 2 axt Brownian motion. This is the general Fokker-Planck equation for this general B and general A. Okay, B is the vector, A is the diffusion matrix. So you have this is so-called the Kolmogorov general Kolmogorov forward operator. But in algorithm Y, you can treat this A as kind of preconditional to your skin, right? A times some Brownian motion, right? B essentially depends on your pi. It's kind of a vector field you want to create later. Now assume that there exists some invariant distribution pi with an explicit formulation. My question is like, how do you convert to invariant distribution? Okay. I say, what do you mean by this assumption? I have many examples in the literature. People already create a lot of different stochastic differential equations. Later I will show you. Okay. So essentially, let's make it more concretely. So we want to study the so-called entropy dissipation for non-gradient and degenerate stochastic dynamic theta. Now here, non-gradient is very related to the work we are doing with Li and Wuchen, right? This non-gradient Westerton gradient flows. And so this is the major difficulty is like it's degenerate. Okay, the good algorithm, sample algorithm, you need some degeneracy. This one can accelerate your spatial gap. And it's non-gradient. In physics, in computation, people like this non-gradient direction. Okay, gradient direction is very direct to the target, like overdamped Langevin. But many days you are oscillating around, maybe you are converged faster, right? So, so if you go converge to your direction by gradient descent, maybe that's the best way. You have to zigging around, then you go. It's faster. I'll give you an example on this. Okay. Now, this is our analysis. Before I go, I tell you just a standardizatory second order operators in generalized optimal transport space. Okay. In this kind of proof, we don't make assumptions. Like say, I assume Vlasov-Fokker-Planck exists. I assume this Planck or this degree exists. If you do that, you almost say it works. Okay, before you prove it. We start from beginning. Just give me the equation. I write down my condition. So that's the interesting part. Let me show you the result. Before doing that, let me recall what do we mean by optimal transport operator. Why optimal transport come in, right? Optimal transport is a very useful mathematical tools for way to study stochastic algorithms. Why? I give a really quick direction on this. How many of you know optimal transport before? Raise your hands. Oh, everyone know it. So I'll be even faster. So essentially, it is a way to measure distance between rho 0 and rho 1. And suppose I have a density with this intensity, I record the density. You want to find the a continuity equation, try to map from 4 to y, like by a map function, you do some expectation of vector field square. Then you want to try to minimize among all the vector field this kind of shape is correct. Then the value between it give you rho 0 and rho 1. And this D is also kind of way to measure the closeness between rho and the pi, between the two given densities. Now behind this, I have to say there's so-called density manifold formulation. That's if you do optimization, you know all this kind of Riemannian kind of thing happens behind this formulation. And it's very useful to do the convergence analysis. Let me be a little bit quick on this so-called optimal transport matrix. Okay, so informally speaking, the optimal transport matrix means when I do Taylor expansion for my Riemannian distance, for my optimal transport distance, I get some bilinear form. This bilinear form will tell me a lot. So essentially, it is rho dot equal negative divergence rho gradient, and it's inverse. Okay, mathematically we call it H negative 1 rho space. Okay, so then you can write it as by its dual variable, which means you write the phi as rho dot, you can get the so-called gradient phi 1 times gradient phi 2 times. So essentially, you get a bilinear form when you do Taylor expansion on this. So for this optimal transport distance, this is very essential. Once you have a Riemannian structure, you can try to. This time I will tell you this stochastic dynamics. The sampling algorithm is essentially a Riemannian optimization analysis problem. Okay? Convex analysis problem. So given a metric space P and J, there's an optimal transport type calculus method. Okay. Namely, we just consider the first order operator and second order operator. Now I call this transport information geometric analysis. Okay. So we want to analysis the Hessian operator. I won't tell you the rate. Now we try to design a so-called TGAR method to study non-gradient degenerate SDEs. Okay, let's continue our exercise. So the Western gradient flow of energy function is as follows. It's negative of your metric operator inverse times the so-called the classical derivative, L2 derivative. You get the divergence rho gradient differential. Now let's practice on this scale divergence, give you more insights. If you are first time see it, double practice this first order picture. Okay. So what we do is the follows. You have your KL divergence, rho log rho over pi. And you compute the L2 derivative for this guy in the score function, log rho over pi. You have divergence rho gradient log rho over pi. Then for the log function, you can do log rho minus log pi. Now, divergence rho gradient log rho is very interesting because rho gradient log rho equals gradient rho. So you have the so-called, you take additional divergence, you get Laplacian. For log pi is just gradient way. So negative log pi, gradient log pi give you gradient. So this slide basically tell you a lot of story behind it. Okay, now let me summarize. So if you first time see it, I will say double compute this. Later on, I will use it almost 40 times. This thing is essentially telling you when you have your KL divergence, when you look at your sample algorithm, you can see it from the optimization angle. I optimize what? I optimize the KL divergence. Right? This is my objective function. And I time some, take the derivative, I time some preconditional, and I go. Okay, so it's that, so it's essentially preconditional gradient descent, or it's kind of like Riemannian gradient descent for your, KL divergence. Okay, so basically, your stochastic algorithm somehow connects to the Riemannian optimization. Now the game is how can we use this thing to do convergence analysis? Now let's recall what we have seen before for this, this negative log concavity. So what do? You do the first of the integral dissipation. You use this operator. It's very clean by integrating by parts. You get a gradient log rho square times. Okay. If you are familiar with Riemannian optimization, this is the first step. You can do the Lyapunov analysis, right? You decay your Lyapunov function, you get something negative. Now the second step is more interesting. If you compute the second order derivative, you will essentially get into an operator, which by linear form, which is what in your question, you have something positive plus some negative Heisenberg log pi. Okay, that's the negative Heisenberg log pi will tell you the rate. Now this is gamma, this is in literature, it's called gamma 2 operator. It's a bilinear form, which is essentially a particular optimal transport second order operator combined with your entropy. Now, once we understand this, you know the algorithm much better. I have to say this is more complicated than what you have before, it's second order derivative, but it contains a lot of convexity informations. Okay, now let's go back to our question. For a general Fokker-Planck equation, which I mean is in this form. Now, I think it's there exists a smooth invariant distribution pi satisfies this condition. Okay, essentially I want to plug in pi into it. Now, if b negative v a equals 1, it's definitely, pi equal negative v is a solution. Okay, so essentially to create a general stochastic differential equation, you need to satisfy this condition. Okay, I believe in engineers, in physics people, they already have a lot of examples tell you what is b, what is a, give a lot of parameters. Now the question here, suppose B and A is given, how can we, study this convergence? Now before I start, I have to say, we have to figure out which part is the gradient direction, which part is non-gradient direction, okay? This is essentially figure out which part we can use classical study, which part we need to create a new, a way to understand it, so-called non-gradient direction. Now this is so-called decomposition. The gradient and non-gradient. In computational fluid dynamics, actually, we have a name for this. For non-gradient direction, we often call it a flux direction. What do we mean by this? Now, essentially, you can intentionally write down your Fokker-Planck as follows. At the beginning, it's like this, right? Some second order operator, first order operator. Now, once you do this decomposition, it becomes very simple. It becomes divergence rho AA transpose gradient log rho over pi. This part is very close to the Western gradient flow, right? The only thing different is you have A is your diffusion matrix, right? Now, the rest term, I call the gamma. Basically, you just write down this operator, it's AA transpose gradient log pi minus B or something. You can easily check, if I write this way, I plug in rho equals pi 0, you can easily check divergence pi gamma equals 0. Okay. So you see, there's a lot of magical property behind it. This is the so-called generalized entropy flux metric condition. I thought I invented it 2 years ago with Professor Usher at the CT. Oh my God, I created something totally new. Then Professor Jianguo Liu tell me, okay, I did this, and many other people did it. This is so-called the generic system or pre-generic systems. My good friend Hong Dong also work in this direction. Once we have papers, they also say, I did this before. It's okay. We do computation and convergence, so nobody do that. But anyway, this is a way you can write down your direction. The direction is the right hand of your Fokker-Planck equation into the so-called gradient direction. And this is the non-gradient direction. Okay, non-gradient is something that your entropy will be your KL divergence will be conservative along these directions. This thing is helpful actually in algorithm. For gradient direction, it gives you some convergence to the solution. For non-gradient term, also contribute some convergence part to your solution. So the combination of them will give you the convergence analysis. Okay, you may think it's very abstract. Later I'll give you examples. In particular, underdamped Langevin dynamics, then you will feel much better to see this picture. Okay. So that's my main result. So I will assume the following thing is correct. I will design some matrix Z, and Z transport times the gradient A is lived in the span of A. Okay, each A1 here is the row vector. A1 transport become a column. Z is some other vectors. So later I will define what is Z transport gradient A. Okay? So if A is a constant vector, this is always true because gradient A just becomes 0. So it's always living in a span. But if A is in the false space, if you don't have any degeneracy, this is always true, right? But if A is the metric function only depends on first n variable, then you just need your Z depend on the n plus 1 to n plus m variable. So this is a very easy to check assumption. Then I'm able to give you the generalized negative log concavity condition. It's given by the following formulas. Each formula has a meaning. I'll tell you later. It's essentially a lot of metrics. I call it R. Don't worry, I'll tell you what is R later. It's a lot of metrics together. You do a summation. And this RA or R gamma Z is tell you the non-gradient direction. So if your R is positive definite respect to A transport plus Z transpose, then your KL divergence will converge to the solution exponentially fast by this lambda, 2 of this lambda. Okay, and it doesn't depend on your initial condition. It's a global convergence result. Okay, now what are them? RA, RZ, RP? That's the complicated stuff. This is, before I go ahead to say, for some special case and be studied by our previous authors, in particular Breton and Gaffarello, they studied for the gradient flow case, and with a very restricted condition, we go over it. And Arnold and Eric Cullen and Ju, they have for the non-gradient flow, they study a lot, but for the non-degenerate A. Okay, when A and Z are constants, actually Arnold and Abba study for this already studied it, but for the linear case, they prove that's the best of it. Okay? But they still public. I mean, their paper already 7 years, still undergoing review. Okay? Anyway, for our case, we are most general case. Give me any A, any B along my Z condition is satisfied. This is I will give you a bit. Okay, where's my? Oh, this is my tensor. Sorry, this is RA, RA, and R gamma. So it's essentially just a matrix. Okay, for different examples, I will give you more details how this matrix look like. Okay, so if A is 1, let's say the simple case, A is 1, B is negative V. This one, only this one survive, RA and R survive, and this just give you negative Hessian log pi. So it's a generalization for your Hessian log pi. Now I can tell you a detailed relation between A and the Hessian log pi and B, how they play together give you the rate. Okay, but it's complicated. I mean, this is once you have a depends on x, you will have the second derivative of a somehow in this picture, because this is in geometry people call it the Ricci curvature. If you are on a gradient system, Ricci curvature is the second derivative on a diffusion matrix. But to understand it, I mean, to be user of this, you must write it out. Okay. So I argue with geometry people all the time. You must write down what you do, right? You see, Ricci curvature. They don't tell you anything. You have to not tell me the tensor. This is the tensor. And now I can generalize by any z, any b. That's a beautiful stuff, right? Don't worry, I will give you detailed example. This is, in general, you can write it, but you have to use the example to understand each individual term. But essentially, it is one coming from gradient part, the other part coming from the non-gradient. That's what we call different tensors.
Wait, there might be a question from home. I see there's a question and answer.
Yeah.
Okay. Let me
Activate chat.
actively check. Oh, no, not me. Maybe you. Okay. Let's continue.
No chat in the webinar.
Oh,
Yes.
You can put questions in the Q&A box.
I see.
Let me tell you the main idea. If the first time you say it, it's okay, but the main idea is very simple. So very optimization oriented idea. So what you do is follows. We create a so-called RAZ row and pair. What is RAZ? In optimization, when you want to prove some degeneracy kind of convergence, you always consider so-called a functional RAZ row. It's a bilinear form of this thing. Your slow function times AA transpose plus VZ function times gradient log row over times row. Yeah. So basically, it's very easy to explain. It's a VT the norm. Z is something you create. Okay. It's a VT the norm of your gradient log row, like something quadratic. Now, without the Z, I tell you this method doesn't work, okay? Because A is eternally degenerate. It don't contain all the information about this gradient operation. So we just pick, we add an additional direction, try to create a Lyapunov function. So if this one decay, later on from this step, I will show you, you get this convergence rate. Okay, that's the idea. It's very easy idea, you just plug in additional. Yeah, okay. This intuition based, and later we check, okay? This is the hard part. This is some direction you pick for your algorithm. Okay, for a good question, like what is the best Z? That's the other technical stuff. Okay, but without Z, it doesn't work. Because without Z, yes, your KL algorithm will decay by A, but A is too degenerate. So if you continue compute derivative over this guy, it will not decay. I mean, somehow it may increase. So it's not purely a decay system. You need to additional Z to further control this dynamics. For degeneracy, somehow to go to some eigenvalue direction, it will not decay. The Z will help you to see it. That's the mathematical insights. Okay. But what is the best Z? Okay, so that's really hard mathematical question. I'll show you why it's hard. Okay, I'll give you some example. Now, once you do this, now follow this. Essentially, you get some modified Heisenberg matrix. Modified Heisenberg matrix give you the R, something squared plus R. R is this RA, R pi, all this stuff I'm going to show you before. Okay, now if R is point definite, I will convert exponentially, following standard procedure. Now, how can we get this in? This is the interesting part. I will skip a little bit. Essentially, RAZ is this guy. And if you come to derivative, remember this AA transpose term, we are given a classical Hessian operator, weighted by A. Okay. Now you have additional this Z pi and RIZ coming from your non-gradient direction and coming from your pi. Okay. So this thing takes us several years to figure out, this is the correct way to compute. Even you know it, how do you organize it into a, you have to make sure you get the convergence rate, right? That one takes time. Here, gamma 2Z, and gamma are designed by linear forms coming from second order calculus in this space. Okay. So if we are still young, it's good time to learn some calculus in the data space. It's just reminding optimization stuff. Then you will see a lot of interesting, magical time. But if A is non-degenerate, then 2 is 0. Okay, if you don't have, let's say A is non-degenerate, you don't need a Z. So you just just need the gamma 2. That's enough. But you still need the RA because that's for non-gradient direction. Okay. Now if B is the gradient vector field, you don't need the 3. Okay. But if A is non-degenerate and B is the gradient, you don't need these two newtons. Okay. Everything can be defined very interestingly. I will skip the details. Essentially, it's some beautiful bilinear form. You can check in the end, you will get the operator will derive. So your operator can be designed in a very beautiful way, which tell you it works. Okay. So the Fokker-Planck equation is a very magical equation, allows you to a lot of interesting analysis. One reason is because it's linear. Okay. But essentially, later I will show you this one can go beyond the linear case. I can also do some mean field Langevin dynamics using similar techniques. Okay, I skip this. I directly tell you suppose you can do that. Suppose you have R larger equal to lambda, then you have this decay from the groundwork. Now let me do examples. Okay, that's more interesting. Now in general, you can consider the following process. So in the old days, I give you B and give you A. Now I write B and A more closely to pi. So essentially I write this as follows. Dx equal to negative A transpose gradient V plus some derivative on A, correction term, minus gamma plus square root of 2A Brownian motion. I assume my gamma satisfies the divergence pi gamma condition, which is divergence E to full A gamma equals 0. There are many choices of this gamma. Okay, so if my dimension is 2-dimensional or 2n-dimensional, I can choose my gamma become anti-symmetrical vector times a gradient of pi. Okay, so there are many ways we pick this gamma. And if gamma is 0, I will call this kind of gradient dynamics. It's gradient Western gradient flow time. Okay. Now for simplicity, let's say A is diagonal, or the A diagonal only depend on xi. In this case, my condition can be the condition I show you can be right very explicitly. Okay. So it's easy to check if this is true. You get the invariant measure pi is 1 over z to negative. Okay. So essentially, this is my Rx. So this is the condition. It's just a modification of the Hessian. It's not negative log concave condition. This is a modified Hessian operator. And you have a lot of other terms coming from your gamma, your A, and your Z. Oh, there's no Z even. Okay, let's consider a simple case. Okay. And even on 1D, it's much more, it's even more clean. In 1D, okay, all the algorithms should start from 1D or 2D, okay, before I go to any D. So in 1D, it's essentially a Hessian condition. Okay. So if A is 1 and gamma is 0, just V double dot, negative Hessian log of pi, right? V double dot. If A is 1 and gamma is not 0, you get something like this. This means if I can pick my gamma in such a way that negative gamma dot is positive, I will accelerate my algorithm. Okay. I mean, usually you have to solve some equation. What is your gamma? You have to solve a PDE or ODE, right? Divergence pi gamma equals 0. So if you can solve that one, figure out a very good gamma, you may accelerate your algorithm. Okay. In this stochastic sampling problem, if V is non-concave, what should we do? If V is in the Hessian V is negative definite, you are not have a non-convex something, non-convex of this V function. What should we do? Now we hope this gamma could help, right? Negative gamma prime may be positive. Try to help this convergence. But that's a hope. I don't give you the example. It's complicated. You have to solve the other ODE or PDE, try to figure out if it works. But this is possible, hopefully. And then you have, for different settings, you have different way of writing it. Okay. Now for example 2 is so-called underdamped Langevin dynamics. This is my favorite example. Michael Jordan and his team, EMR, from the UCSD, write a paper called "Is there a natural method for MCMC sampling?" Okay, I'm the reviewer for that. So the major reason follows. That's the reviewer experience motivated me to do this, because I must understand how can we accelerate my sample. In optimization, people believe second order dynamics works. Second order means the following: you have dx dt equals v, dv equals some, this is called the damping parameter t, and v minus the gradient of u plus square root 2 of t xt Brownian motion. Now, if t is a constant, okay, then that's the so-called the constant variable on the underdamped Langevin dynamics. Now, in my situation, I try to consider very general t. T could depend on x, okay, for variable case. Now, in the algorithm part, we want to see, is this better than the overdamped Langevin? Can we get a faster convergence rate? Can we go over this, this negative log concave condition? Okay, at least in their period, in my period, I don't know. It's a very challenging problem, but I believe there's a chance if we use more parameters and we organize it better. So for this talk, I tell you, for this one, we can study it. You just write y as x and v, you write d b, y as by and square root a y d Brownian motion. Then abstractly you have b, you have a, and you can write down the Gibbs measure, the 1/2 v squared plus ux. Okay. So essentially, we can understand the convergence rate as follows. Now, this is the gamma. Gamma is non-gradient direction. You can write it carefully. It's a G, it's anti-symmetric matrix times this gradient x of your Hamiltonian. Okay. Then divergence pi gamma equals it. Okay, it satisfies my condition perfectly. And this is one of the classical example in generics. Okay. So then this is the condition. Okay, this is just a 2D times 2D matrix. In 1D is 2 times 2. Okay. So essentially just how you organize Heisenberg log pi and A. Okay. So essentially you can write it very explicitly. Actually, we did it when A is constant, or when A and X dependency is very easy. This is computable. Okay. Now, if it's definite, we have to converse with it.
There's a question in the chat.
Yes. This one more. Is R lower order than Fisher information? R a lower order derivative of Fisher information? Does the Hessian dominate? Oh, that's a very good question. So this R essentially it is coming from the derivative of Fisher information. Now you have to organize your formula to get this matrix. Basically, this is a very technical and important question. So essentially, it's this step. You compute derivative of Fisher information, and you pick up something, something that is positive. You take the positive part. This is the rest term give you. And that R will give you that matrix thing. Okay. So essentially, you have an infinite dimensional spectral gap given by your Fokker-Planck equation, right? The Kerber-Log formula operator. Now, using this technique, you get a finite dimensional matrix function. And if you understand this finite dimensional matrix function, you understand the spectral gap problem at the beginning. Does it answer your question?
You will not hear this.
Okay. Anyway, we will talk this after the talk. Let me show you some examples.
Except this, so
yeah,
you do maybe press answer live and then dismiss answer live.
Oh, okay.
And then done. Okay.
Yeah.
Now you can close the window.
Oh, okay. That's very good. Very advanced technology. Yes. So this is the formula, and actually we can test it. So this is the good part when we do some computational math and applied math. You have some formula. In general, it's very hard. But why don't we compute it to see what happened, right? You pick some direction and you check this matrix function. Okay. The computer assisted proof. Why don't we do that? Now then everything is computable. Okay. You have such a clean matrix. Now this is the eigenvalue computed by the computer. So with T the 1, it's very everything easy. You get roughly 0.1 convergence rate. If your diffusion, your Tx is constant and this U is just 1/2 x squared. In this simple case, the convergence rate is given by e to negative 1/10. So it's slower. If you do, this just tell you one example. If you don't pick a good parameter, it's slower than overdamped. Okay, this also coincides with EMI and Michael Jordan's paper. They also get the 1/10, so it's slower essentially. But now the really game is like we must pick the best parameter to accelerate it. Okay, so people have evidence this could accelerate in experiments, but you need to pick the good parameters. Try to give you better eigenvalue in the hashing in the R. Okay, now we try some other example. For this t is some function. Sorry, when beta is 0.1, t is also 1. We get some other rate to tell you our formula is more general for this example. And we can also study for
5 minutes.
okay, enough. So you have for some variable dependent, t. People also believe you have to use some hashing inverse to precondition this diffusion matrix. They will also try that. Okay, but you will give it by some polynomial. They will just compute this rate. So sometimes it can become very negative. So which means, okay, you have to be very carefully choose your diffusion matrix. So this diffusion matrix must talk with this hashing matrix and try to get the best convergence. Okay, we know A equals 1 is very stable, but stable doesn't mean it is fast. To get a fast A, you need some A talk with pi by some differential equations and this R matrix. Now the second example we do, maybe some of you know the family is called stochastic differential equation on Lie groups. This is essentially so-called quantum stochastic differential equation. Quantum means it's a particular A, and A is some given by some variable dependence. It has a very structural linear algebra behind it. Okay, so essentially it's still the same picture. Let's pick gamma equals 0. It's a gradient vector field, and A is still have a very strong degeneracy. Let me give you one example. This is a good example. So called the Heisenberg group. Okay, this is the first example in quantum computing. Okay, everybody believes this is works, right? But this is the simplest example you can believe. That's this three-dimensional matrix. A is in R 2 times 3. 3 rows, sorry, 2 rows, 3 columns. The 1, 0, negative y/2, and 0, 1, x/2. Okay, and in this case, I pick 0, 0, 0, 1. Then you can write down your hashing operator. Now it's a very challenging job to know what is the lambda. I will tell you. So if it's on global domain, it's lambda it should be negative all the time. We try very hard to say when and where you can get the lambda. So it's still ongoing result. But if this is true, you have the experiment. So when you work on some particular example, it's even harder than general one. So that's this kind of problem dependent. You can also do the displacement group with the other Lie group structure. Okay, it's just very degenerate, A matrix. But in the end of the talk, I talk about so-called mini field on the Langevin dynamics. So I believe you don't have similar projects. So all the dynamics is particular case of generic. So the proof here should works. Now for this particular example, it is I chose this one because Valani and Jose McKay did this. That's they do it on gradient flow case. Gradient flow with overdamped Langevin dynamics. Overdamped mean field Langevin dynamics. I work on underdamped one, so which means I have x v at this term. Okay. For this one, you can write down this kinetic Fokker-Planck equation by this weighted, formula, weighted by this formula, and then you can do a similar job I did before. You can rather use generic to. This is also well known by my friends and myself. This is very useful in convergence analysis. Okay, that's my part. Okay. So essentially, you can write W FA transpose gradient XV differential of your energy and W F gamma. Your energy is given by your entropy rho log rho plus some, this guy is your Hamiltonian term, is linearly on F, and some quadratic terms. Okay. And then you can figure out the gamma equal to J, actually J is antisymmetric structure times differential term. Okay. when we do computation a bit later on, if you can capture this structure, it definitely give a lot of benefits. In my proof, I say this. Okay, let me show you.
Just how many more minutes?
1 minute. Okay. This is the matrix. Very similar one. Just don't worry. This is everything the same. The only thing different, you have W, you have interaction kernel. That's why I have a lot of X, Y dependent. Once you have it, you have the exponential decay for nonlinear energies, quadratic energies. Okay. Now the game is like give me your sample algorithm. Can we write it into this generics? I believe so because many problems have structure. Right? So this is the same. Now I have some example like how do we pick W, give you lambda is technical. Just they become a matrix estimation problem. Very interesting. Okay. Now that's my talk. So essentially I want to say it's a TGAR method for stochastic analysis and algorithms. So far it's more on analysis. Right now I'm trying to use some inverse problem technique to create some A. And there are several questions behind it. What is the optimal choice of this oscillatory directions? So how can you pick Z? We don't know. Okay. So far we try and we see. Give me your algorithm. What is the best Z? That's on the good direction. And then we will design some fast scalable AI algorithms. Basically, this is a structure given by the generic gradient and non-gradient. Can we build a better score matching method, right? This is that's why we need you, right? Yeah. Then we have a flux gradient flow function inequalities and complex analysis. So there's a lot of things behind the optimal transport can be done for a much general setting. This is very exciting for the future work. Thank you.
Any questions?
Yes.
I'm interested in the thing you said about Nesterov and MCMC.
Yes.
Was there an answer?
The answer so far, no answer.
There's no answer, but it should be in the Fokker-Planck equation, not in the.
Yes.
That's where you should see the second order terms come.
Yeah. So far, we double check the Michael Jordan and EMR's proof. It's actually very similar to our proof. In the end, we say it's slower. If you pick the damping parameter, the T is 1. It's slower. So for the overdamped Langevin, if you the constant rate is 1, then they become 1/10 in the proof. Okay. So
there's this thing like, if it's a strongly convex function, you should use heavy ball, which is like the constant damping.
yes.
If it's not strongly convex, you should use Nesterov.
Exactly.
But you can choose the heavy ball damping to make it slower than gradient. It's tricky.
Yes, once you have time dependent, it's much more complicated calculus here. It's more interesting. My collaborator and I try to create it. So it's very hard to say it's good, okay? But if you say it's some rate, we can do it. We studied some time dependent case right now, but so far the optimal one is much exciting, but it's very heavy work. Okay. So we could talk later. Yeah.
Any other question?
Yeah.
Okay, then let's thank Wuchen again.
Yeah.
I'll spend a lot of time.
Okay, yeah, sure.
No worries.
Yeah.
Hello, Georgia.
That's hard. So far, we only prove the KO.
Georgia, should I just
quit?
quit the seminar, webinar?
I don't know anybody did that before. Yeah. There's a different techniques. I do something there with A and B.
Just stop recording.